measure the height.
Yeah, no, measure the width from here to here.
Laminated overnight on a CNC cut jig. Hey, Jonathan here at Colfax Math. Today I was going to go over three-dimensional graphing, X, Y, and Z, midpoint, and the distance formula in 3D. So we start right here in math class with a number line called X. I don't know, that might have been back in 4th grade. And then when you have 1 plus 2, you move down the number line. And then you stay there for quite a while with X, and then you go to Y, two-dimensional space, and then now you have a coordinate, say 2, 4, over 2, up 4, that's always X, that's always Y in alphabetical order. And then now what we're going to do is add three-dimensional space. So if this is Y, this is X, the new axis is Z, and it comes straight out from the board like this. So the way you draw that is like this. So this Z axis is coming straight out. Rather than have 4 quadrants, I now have 8 octants. And now if I had a coordinate, say 2, 3, 4, this would be my X value, my Y value, my Z value. Like everything in math, it kind of makes sense. So this is X, Y, Z. I would label those points on my axis. I would be 2 over in X, 3 up in Y, and 4 down in Z. And then the key to drawing this is you're going to draw a box on here, just making sure that all your lines stay parallel. So if this is one edge of the box going up, this is its second edge, the same length as that. This is the back side, so this stays parallel. So there's the back edge, the top edge, I don't know if you can see it there. So I have a box here where I am 2 over on the back of the box, 4 out from the board in Z, and 3 up. So it really looks like this. I don't know if you can see that box, right? Where if the coordinate is 2 in X, this would be 2 right here, 3 in Y, and 4 in Z, so the depth of the box. So it's hard to see because it's three-dimensional space, and we're just trying to represent what it would look like. Let's go to my desk and I'll go over midpoints and a three-dimensional Pythagorean theorem. Okay, let's take a look at another three-dimensional coordinate. Let's say now 3 over in X, 2 up in Y, and 5 out in Z. So that would be 3 over in X, 2 in Y, and 5 out in Z. I would stop it and see if you could sketch this out. So this is going to be my height of my box. I'm going to move that over there. This is parallel to that, so that's the back edge. This is the side of the box, or the bottom back. Just like that. This stays parallel to that. There's the bottom of the box, so I have 1, 2, 3, 4 edges, and then this will stay parallel to that. I'm a little off there. So there's my box there. This coordinate right here is over 3 in X, over 2 in Y, and up 5 in Z. So this little box 3 by 2 is flat on my desktop, say, and then it comes up out of the page a unit of 5. The midpoint between 2 three-dimensional points, so if I'm going to find the midpoint between 0, 0, 0 and 3, 2, 5 is just the average of the two values. So I take my first X value, I add my second X value, and I divide by 2. So this is the equation for midpoint. I take my first y value plus my second y value divided by 2. So that's my midpoint formula in two-dimensional space. And then to go to three-dimensional space, I just add my z-coordinate and divide by 2. So I add my two z-coordinates and divide by 2. So to find the midpoint between the origin and here, I would take 0 plus 3, divide by 2, and get 1.5. To find the average of my y values between the origin and here, 0 plus 2 divided by 2 is 1. 0 plus 5 divided by 2 is 2.5. So that's the midpoint between the origin and here. Let's say I want to find the midpoint on this diagonal right here. So this coordinate right here would be over 3. In y it would be 0. And in z it would be 0. So the midpoint here would be 3 plus 3 divided by 2, which would be 6 divided by 2, which would be 3. 0 plus 2 divided by 2, and then 2.5. So that kind of makes sense. If you look at this point on the side of the box, I could see in the x direction it would still be over 3. In the y direction it would only be up 1. And in the z direction it would only be at 2.5. Okay, next is three-dimensional Pythagorean Theorem. And before I go over that, let me just go over the two-dimensional Pythagorean Theorem and the distance formula. So if I'm in x and y in two-dimensional space, and I have 2 points on my Cartesian coordinate system, let's say this is over 2 up 4, and this is, say, over 6 up 10. And I want to find the length of this line. Well, I could just draw on a right triangle and see that this leg would be 4. From 2 to 6 is 4. And then this leg right here, the vertical leg, would be 4 to 10 would be 6. And then I could use the Pythagorean theorem to say this is c. So 4 squared plus 6 squared equals c squared. 16 plus 36 equals c squared. 52 is equal to c squared, or c is equal to plus or minus the square root of 52. That's an exact value. I discard the negative because we're talking about the length of a side. And that kind of makes sense, right? That's a little more than 7. I'd expect that to be a little more than 7. Well, the distance formula is the square root of the difference in the x values, so x2 minus x1 squared. Well, that's what we did here, right? We did the distance from 2 to 6 is 4, and we squared it, plus the difference in the y values, y2 minus y1 squared. Well, that's what we did here. We did 10 minus 4, 6 squared. And then we squared them, we added them, then we square rooted them. So the distance formula is really the same thing as the Pythagorean theorem. And in three-dimensional space, that's true as well. So using the distance formula here, I would do 6 minus 2, 4 squared, plus 10 minus 4, 6 squared, and then the square root of 52. Okay, in three-dimensional space, right, in three-dimensional space, this is a little hard to see. Again, this is y and x. And we had that third axis coming straight up. We draw it here as a z-axis. Right, let's do a different one now. Let's go 1 in x. Negatives work the same way. You're just over here is your negative values of x. Down here, your negative values of y. And then z negatives are going back into the board. Let's say 1, 4, 6. So I go over 1 in x. I go up 4 in y, and out 6 in z. Again, this line needs to get transferred here. This line transferred here. There's the back of my box. This right here goes there. That to there. So there's the back side. the back left side, the bottom. Draw it this way. So there's my box there. So if I want to find the length of the diagonal from the back lower left corner to the front upper right corner, that line right there, the first thing I'm going to do is find the length of the diagonal here. Well, the length of that diagonal there, this side of the box is 1, this side of the box is 6. This is a right triangle, so this thing right there, c squared, is equal to 1 squared plus 6 squared, or 1 plus 36, 37. Square root of both sides, c is equal to square root of 37. So the length of this is square root of 37. Now I'm creating another rectangle, I'm creating another triangle right here, where this is one of the legs. And then this is the hypotenuse of this right triangle. I know it's hard to see, but if this is the bottom leg, square root of 37, this is a vertical leg, 4, this c value is the square root of 37, this vertical leg right here is 4, I need to find that hypotenuse in that right triangle. So I have 4 squared plus root 37 squared equals, we'll call this c sub 2. C sub 2. So then I have 4 squared, 16, plus the square root of 37 squared, 37, equals c squared. 40, 53 is equal to c squared, square root of both sides, and this long diagonal is the square root of 53. And that's what leads us to the three-dimensional Pythagorean theorem, which is going to be the square root of the difference in the x values squared plus the difference in the y values squared plus the difference in the z values squared. I say three-dimensional Pythagorean theorem or the distance formula because, as you can see here in two-dimensional space, the Pythagorean theorem and the distance formula are the same thing, and that is also true in three-dimensional space. So if I'm using the three-dimensional distance formula here, I would have the difference in the x's, so the difference between 0 and 1 would be 0 and 1 would be 1 squared. The difference in the y's, 0 and 4 squared. And the difference in the z's between 0 and 6 squared. And it would be the same, square root of 53. So the Pythagorean theorem works in 2 dimensions or 3 dimensions. The distance formula correspondingly is kind of the same for both. You're just adding a third coordinate, x, y, z. So now we're adding a third coordinate, z, in three-dimensional space. So hopefully that helped a little bit understand three-dimensional graphing, three-dimensional midpoint, three-dimensional Pythagorean theorem, and the distance formula in 3D. It's actually really useful for anything in manufacturing and CNC manufacturing, anything in aviation or flying or navigation at sea, because very few things stay flat on the plane. Almost everything's in three-dimensional space. So this is one step away from doing vectors, where you add both magnitude and directions in 3D. And those components will be I, J, and K in vectors, but I'll save that for another video. So this is Colfax Math. Thank you for watching. If you liked the video, hit like. If you want to see more videos on applications of math and all things math, hit subscribe and get the bell for notifications. So thank you.